I'm going to talk about quantum entanglement, an idea that goes back many decades on the structure of quantum mechanics. But a very interesting development of the last 20 years is what was viewed for a long time as just a philosophical idea only of interest to people thinking about just the fundamental foundation of quantum mechanics rather than practical physicists to go and measure things in the laboratory. But in the last 20 years, it's become clear that the idea of quantum entanglement is not just some theoretical playground, but it's something of extreme importance in understanding many interesting phenomena. And what I'm going to present are just two basic phenomena and try to give you a flavor of how quantum entanglement affects the behavior of really macroscopic matter. So this picture here is a picture of a superconductor. It's from an article I wrote in Scientific American. And these are the poetic words of the editor on what's shown here. It's a superconductor levitated by an unseen magnet in which countless trillions of electrons form a vast interconnected quantum state. So I want to take those very descriptive words and make them a bit more precise and get you a sense of why is it we think we need to use these strange ideas to understand this phenomenon. So the idea of quantum entanglement goes back, as I said, a long time. And in particular, Einstein didn't find it palatable, and he called it spooky action at a distance, since then, people have suggested various experimental tests that one could perform to test whether quantum entanglement even exists for microscopic particles. And now there's very little doubt that it does. And here's a report in the New York Times about a year ago of an experiment in the Netherlands showing testing what's called Bell's inequality and really proving in some sense that spooky action is real. Okay. So with that general introduction, what I'm going to do is just assume you haven't heard about quantum mechanics before and try to just get the idea of quantum entanglement across from its very basics. Okay, so let me begin with a description of a classical experiment. That's something in principle you could do in your bathtub. So here you have, sorry, I'm getting used to this whole configuration. You have water, and you're shaking the water near these two inlets here. And that sets up waves. And as the waves propagate, they interfere with each other. So there are, say, the bright regions where the wave coming from one outlet has a maximum, and so does the wave coming from the other outlet. And therefore, that region remains bright. And conversely, there are other regions where the waves cancel each other out because one is up and the other is down. So if I measure how much energy I'm depositing on the screen here, what I notice is that there's these black points, let's see, where things are generally brighter, and then there are points here where things are much darker. So there's an alternating pattern of bright and dark coming from the interference between these waves. All right, so that's a familiar phenomenon, nothing really mysterious about it. Now, if I try to do the same experiment by sending in particles, say bullets or baseballs or something, you won't see this interference pattern. Rather, you will conclude that each particle goes through the screen, through either the left slit or the right slit, and as a result, you get these two regions in which most of the particles going through either go to the left or the right. All right, so now the question becomes, what happens when you do this experiment with a microscopic particle like an electron? So if you have an electron gun and you try to send the electrons through the slits. So this experiment's been done many times over the last century. And what we find when you do this experiment is that you see an alternating pattern of light and dark, much like the waves in the bathtub. So when you see this, you then conclude, well, the electron must be a wave. I haven't seen an electron, so maybe it's not a particle. That's a misconception. It's a wave, and so what's so mysterious about that? So that could be a reasonable conclusion at this point. But however, quantum mechanics is much more subtle. That's really not the mysterious part that you see by itself. It's not so mysterious that you see alternating patterns of light and dark. What's much more remarkable is kind of indicated in this picture, is that, so is the electron a wave? Well, it looks like a wave from the pattern of light and dark. But on the other hand, when you do the experiment, the electrons arrive one by one, as you can see right here. So if you did this experiment with waves, with electrons, you'd see the dots appearing one by one on the screen. So each electron appears as a single event at a given position on the screen, just like a particle. So you see these bullets arriving, which look like particles, because you just see a singular event at a given point on the screen. But if you wait long enough and measure enough electrons, you find that the pattern of light and dark doesn't look anything like the pattern for bullets. It looks like the pattern for waves. So that's really the heart of the conundrum of quantum mechanics. How can something have some features that are so particle-like and other features that are wave-like? And that's the puzzle that we've been pondering for the last century. And the resolution that quantum mechanics offered to this was something that Einstein in particular wasn't particularly happy with, and said that there's something about the world that we don't understand. Okay, so if it's both a particle and a wave, and you're still bothered by that, you can now ask the question, well, so you're telling me it's a wave, but it's really, but it arrives like a particle. But I can tell if it's a particle just by looking at the electrons before they go through the double slit. So let me look for the electrons here. So imagine I have some kind of magic torchlight, which tells me whether a given electron went through the left slit or the right slit. So if you try to do this experiment, and again, people have done analogous experiments, so each electron goes through, and you know that each electron went through either the left slit or the right slit by the act of measurement. Okay, so then you're very happy. Each electron is looking like a bullet, is going through either to the left or the right. But at this point, if you look at what's happening on the screen in front of you, the interference pattern, the alternate pattern of light and dark, has disappeared. So once you find out which slit the electron went through, it really did go through that slit, that you saw it go through there, and there's nothing wrong about that. But if it goes through one slit or the other, you don't see the interference pattern. So the inescapable conclusion from all of this, most physicists concluded, is that you really have to allow for the possibility that each electron, even though it arrives discretely as a single event, went through both slits. So that's the counterintuitive idea we have to accept. So that's the surprising, that's the key idea of quantum mechanics, that you can have the state of a particle like an electron have really more than one possibility. So I'm just going to introduce a little bit of notation to describe this. So we have this funny symbol called a ket, which simply says that's a state of an electron going through the left slit. And then there's another state for the electron going through the right slit. And in this experiment, the state of the electron, when you're not looking at it, before it goes through the slits, is really the sum of the two. It's left plus right. So that's the central idea, which I've called quantum superposition, which doesn't appear in Newtonian mechanics at all. And it's a brand new idea which you may as well take as a postulate for the way our world works from many such experiments, that it's possible to take linear superpositions of different states. And really the state of the electron is kind of non-local. It's neither the left nor the right. It's both. And so when you're not looking at it, it's in this superposition state. So that's why you have an interference pattern. But it's still a single electron, and it's going to arrive with a discrete event like a bullet. Okay. So now if you've understood that, you've basically understood all of quantum mechanics. Everything else is just an application of this idea. Okay. That's the heart of what, once you accept this, which many people didn't, including very smart people like Einstein, but many young physicists at that time immediately accepted this and started to work out the consequences. And the amazing thing is we're still working out the consequences, and they're all correct as far as we know. We have no one seen a contradiction to this basic assumption. And that experiment I mentioned at the very beginning is one such example. All right, so that's quantum 101. So now let's go to quantum 102, which is quantum entanglement. So now you're ready to understand what's quantum entanglement. It's the same principle, just taken for more than one electron. So let's take 2 electrons. So I'm going to focus on a single electron, say in a hydrogen atom, and I'm going to represent it by an arrow pointing up. That's just an indication that the electron is spinning counterclockwise. And electrons have this peculiar feature that they have only 2 possible orientations for their spin, which determines the magnetic field near them. But we don't need to know any of that. There's an electron which is spinning up, let's say. So now that's a single electron. We're going to ignore the nucleus. Now take a molecule with 2 electrons. So as you probably learned in high school chemistry, in a molecule there's a covalent bond between the electrons. And here's a very crude description of what the electrons are doing. So even in something as simple as a hydrogen molecule, the electrons are entangled, meaning that they're in a superposition state, much like the left and right slits of the double slit experiment. So what are the 2 states? So I had left and right for the single electron. Here I have the configuration where one electron is spinning up and the other electron is spinning down, and vice versa. So these are 2 possible states of the 2 electrons in a hydrogen molecule. And what we know from many, many, many experiments and also computations, that what the electrons do is form this superposition. Neither one of them is up or down. They're both up and they're both down. But when one is up, certainly the other is down. Okay, so they are entangled. So they know about each other. Neither of them decide to point up or down, but they know that if one is up, the other is down, or vice versa. And that entangled state exists in every hydrogen molecule, and really in all other molecules, really. Okay, so that's the entanglement of 2 electrons. So this brings us to the key idea that was proposed by Einstein, Podolsky, and Rosen in 1935 as to why this is even more problematical than the double slit experiment. Really, the point is, once you accepted the quantum explanation of the double slit experiment, this consequence is inevitable. But with this particular situation, Einstein, Podolsky, and Rosen argued that this leads to even more strange phenomena that can't possibly be true. So imagine you could take this hydrogen molecule and separate the electrons very carefully without disturbing their spin. That's quite hard to do, but you can do analogous experiments with photons of light. But let's just imagine you could do it with electrons. So you separate them really far away without disturbing the spin. So this electron could be here, the other electron could be in Boston. But yet, at that point, even though they're really far away, when their states are still entangled. So there's a single quantum state that describes both of them. It's neither here nor there. That state, just exists. And that state has the property that one electron's up, the other is down. And if this one is down, the other is up. Okay, so that's the state of the 2 electrons. But now, I have my electron here. My friend has the electron, the other electron in Boston. I can now take the electron into my lab and look at it. And when I look at it, I'm going to get a definite answer, either left or right. Just like in the double slit experiment, when I looked at the electrons, I got an answer. It was left or right. So here it'll be up or down. Sorry.
Change the state of the electron?
Sorry?
Can you change the state of the electron?
Well, since you didn't know what it was before, that's not a meaningful statement. All you know is what you measure. So you measure down, say, or let's say here, I measure down. Then I know immediately that my friend in Boston immediately has an electron that's up. So it seems as if what I'm doing here is affecting the other electron. So Einstein didn't like this because it seems as if I do something here, and that information of what I'm doing has to travel from here to there, and that can't go faster than the speed of light. So the other electron could even be in the next galaxy, in principle. But instantaneously, according to quantum mechanics, what I do here affects the other electron because its state is then up if I see down. And if I see up, the other electron is down. Okay, so that's what's called the EPR paradox, pointed out in this paper in 1935, that seemingly the measurement of one particle instantaneously determines the state of the other arbitrarily far away. So what is the resolution with Einstein's objection? Well, the resolution really is that the state of the electron that you're measuring here is not here. When you're measuring this electron, you're measuring their combined state. It's really both here and there. It's highly non-local. And that's an interesting feature of quantum mechanics, that in the double slit experiment, okay, you were just talking about some microscopic distance, but still the electron was in both places. But here we can even make the distances macroscopic with more than one particle, and still the same non-locality persists. Okay, so I put paradox in quotes because it's not a paradox. It doesn't lead to any logical contradictions. And in fact, analogs of this experiment have been done, and they work every time consistent with the principles of quantum mechanics. So in fact, Einstein died before these experiments were done. But today, really nobody doubts that quantum entanglement is real. And the notion of a local quantum state is really something we have to discard. And it can be extremely non-local. Okay. All right, so that's really all you need to know about quantum mechanics. So hopefully I've explained everything clearly. Maybe I can pause for one or two questions at this point. Yes.
So you're saying
We shoot the mic. Yeah.
So you're saying locality doesn't affect entanglement at all?
No, I'm saying the notion of a quantum state is not necessarily local. The two electrons, even though very far away, can share the same quantum state. Now, it's very difficult to prepare a quantum state that you can, know very precisely with particles really far away, which is why you never see these correlations. But if you carefully prepare such a state that you know what it is, then you can make it as non-local as you want. There's no limit to it. Yes? It depends on what you do. If I look at this electron and I determine its state, in other words, I collapse it to be either up or down, then from that point on, they're not entangled anymore. The other one will also collapse, and then their states they don't share anything. What's happened, in effect, is when I look at an electron, it's got entangled with me. And there's kind of a monogamy of entanglement. That electron forgets the other one, it gets entangled with me. Right, so it is correct that you're not transmitting any information. You can't use this to send a secret message faster than the speed of light. We can discuss that further later. Yes?
So what's causing the entanglement?
Well, what caused it was that the way you prepared it. You very carefully took a hydrogen molecule, you carefully prepared it, and you carefully separated it without disturbing the spin. None of those things is easy to do. But if you did it that way, then you could predict something about this entangled quantum state.
Clearly, thank you. But what is the mechanism by which they can seemingly communicate with each other instantaneously faster than the speed of light?
Well, the whole point is they're not communicating because they belong to the same state. So when I'm measuring this electron, I'm not only affecting this electron, I'm measuring the combined shared state. They share something, which doesn't exist here nor there. All right. All right. It's true, but I don't know. I can't explain any better than that. Yes, sure. And the person over there will not know that I've measured it. So it doesn't matter. You will both come to consistent conclusions. You may both, he may think that his state was determined by measurement, or I may think the other way. It doesn't matter. The answer will be consistent anyway.
Is there any friction like in the wave when it's separated?
Any friction? No. So this is if you do the experiment carefully enough. They won't. I think I should move on. So this is great, but okay, one more.
So if I go into the reference frame where I simultaneously measure the
Again, simultaneous is not an absolute concept, but yes.
So I'm in the reference frame where I'm considering them simultaneous.
Yeah.
And I measure this one in the x direction and this one in the z direction.
Okay.
And then I know both the x and z direction simultaneously of one of the spins.
Right. Well, so you can't predict ahead of time what the answer to those measurements would be, but the answer would be consistent with the probabilities we assign from the knowledge of the entangled state. Okay, I want to move on, but that's great. Hopefully you got the basic idea. All right, one last question.
You could send a message by doing what you said earlier, disentanglement, right?
No, so what you can use this for, and this is in fact used today, is to send a message secretly. You can use this for cryptography, but you still have to combine quantum entanglement with ordinary classical communication over a phone line or something. But the combination allows you to send a message secretly.
I mean, message is simply disconnected. It's like a one-bit message, like I've changed.
Right. No, even this one measurement by itself doesn't send any message. Because I don't know what my friend in Boston has done to the electron or what my friend measured. So there's no information. I have no information when I do my measurement. I don't know. He may already have measured. He may not have measured. I don't know. And I measure, I get an answer. I have to call him later to see if we are consistent. That call will take some time. So only then is information going through. It doesn't change. It doesn't transmit any information. It does. That's right. Okay. All right, great. So I've got you all awake. So let me move forward a little bit in history and talk about black holes. So what is a black hole? So this seems like the thing furthest removed from the idea of quantum entanglement. Certainly when it first appeared in physics through the solution of Einstein's equations, no one had any inkling that there were some fundamental connections between properties of black holes and entanglement. So a black hole is a very dense star, and it's so dense that light itself can't escape from it. So light tries to go out of a black hole, but because light is also gravitationally attracted by the gravitational field of the star, it bends backwards and falls down. And this happens, and this would happen if you take some matter of mass m and squeeze it down to a radius r, which is given by this formula, where g is Newton's gravitational constant and c is the velocity of light. So for example, if you took our sun and squeezed it down to a few miles in radius, it would become a black hole. So you just have to make it dense enough. It's not going to do that anytime soon, fortunately. Okay, so now at the time these appeared in the solutions of Einstein's equations, now we have plethora of astrophysical evidence. There are lots of black holes out there, including a supermassive black hole at the center of our galaxy. But of course, most recently, I'm sure all of you heard about the amazing discovery of gravitational radiation by the LIGO experiment from the merger of two black holes. So these are two black holes here in a computer simulation. No one's seen these black holes optically. Actually, the black hole is just a tiny dot in the center. The reason you see this region of black is because the black hole bends light so strongly that it seems as if there's a void over there, but there isn't any void. So here are two black holes, each with a solar mass of about 30 solar masses and radius about 100 kilometers. So that's really a microscopic speck in this picture. And 0.1 seconds after this picture, the two of them merged into a single black hole. Can you see that? Okay. And this cataclysmic event set off gravitational waves, which were then measured in this amazing experiment in Hanford and Livingston simultaneously. Okay. So this is the two black holes that spiral in and merge into a single black hole with the ring down. Okay. So that's beautiful example, beautiful experimental data showing the existence of black holes. All right, so in 1974, Bekenstein and Hawking, this is the famous Stephen Hawking, showed that if you now apply quantum theory to a black hole, this was just purely a thought experiment, you come up with some rather amazing conclusions. Now, they didn't use the word entanglement in their paper, but effectively that's what they were talking about. And so here's one simple way to describe the idea of Hawking. So let me go back to my hydrogen molecule, which I separated between me and my friend in Boston. But let's imagine that this hydrogen molecule is sitting right at the horizon of a black hole. So the horizon of the black hole goes right in between these two electrons. There's probably some hydrogen molecule that's unlucky enough to find itself there at any given minute. Well, what's going to happen? Well, one of them will fall in, and the other will stay out, because one's inside the horizon, the other isn't. So this particular electron is going inside a black hole, and the other one's outside. Now, this electron or this particular quantum object sitting inside can no longer communicate with the object outside. There's just no way. You send a beam of light, it'll just bend back and come back in, because here's the black hole horizon. But nevertheless, if the ideas of quantum mechanics are correct, these two electrons, which are forever separated, unless the second one also decides to fall in, but that's a separate question. But if the second one remains outside and one's inside, they're still entangled. The idea of quantum entanglement still must work. And so they share a quantum state even across the horizon of a black hole. This particular electron can't share any information with the other one, but they can still share the quantum state given their history of being entangled in the past before one of them fell into a black hole. So it was with this type of thought experiment that Hawking argued, and of course if this is down, that's up. So that's still true. If one is up, the other is down, and if this is down, the other is up. So based on this type of experiment, that Hawking argued that a black hole has a temperature, which is called the Hawking temperature. So effectively what's happened is there's an entanglement now, but it's really long range. It's about as far separated as you can imagine two things to be. So it's long range entanglement between the inside and the outside of a black hole. So what's the idea of temperature here? So this particular, now if I'm looking at this particular electron, it can never know anything about the other electron in there, because that's lost forever inside the black hole. So even though this electron is entangled with another electron, that electron has disappeared. So as far as I'm concerned, this electron is randomly up or down, because I can never access the other one. And that's what we call a thermal state. So if you're just tossing a coin, which is 50% up and 50% heads and 50% tails, that's just a random event, which is controlled by all kinds of random perturbations in the environment. So here, if I'm looking at the second electron, since I can never, ever know about the other electron, to me, for all practical purposes, that electron outside the horizon is just a randomly up or down. So it's a thermal state. And what Hawking showed was how he could compute the temperature of a black hole based on this idea of the entanglement between objects inside and outside of a black hole horizon. And there's also an entropy, because it can have these two states. So there's two random possibilities, and the log of that is what physicists call the entropy. So that's then a very simple discussion of the idea of how entanglement is even operational in the study of black holes due to this effect. Okay. And in fact, this has some consequences, although they have never been measured. So this effect has never been measured. So these are the two black holes that are colliding, and then they start to ring down, and very quickly after they collide and merge, the ring down, basically, it becomes just a quiescent spherical black hole. So this very last stage, as it rings down, is, we believe, controlled by these quantum processes and affected by the entanglement between inside and the outside of a black hole. For this particular black hole, that would be few milliseconds. So there's a Hawking temperature, sorry, that should be Hawking temperature. Hawking, h bar is Planck's constant, is a fundamental constant in quantum mechanics. Kb is just a constant that sets the scale of temperature. So it's the h bar divided by the Hawking temperature is about 8 milliseconds, which is really a tiny part here. There's no reasonable hope in such collisions to measure these quantum effects. All right. So that ends the second part of my talk. I've given you a very quick introduction to black holes and where this, this thought experiment of Einstein, Podolsky, and Rosen on the strangeness of quantum mechanics and the existence of entanglement over long distances turns out to have a physical consequence. A physical consequence that if you could get near enough a black hole, you'll see that it's radiating energy, and it looks like an oven at a very cold temperature, though, for these very big black holes. But in principle, it's like a black body, as we say. It's radiating energy at this temperature. So that's a physical, in principle, measurable consequence, and maybe someday it will be measured, but nobody really sees how for astrophysical black holes we could see this effect. All right, so now let me talk about my domain of my research, which is strange metals. That's the third topic in my title. So here's a chemical compound called yttrium barium copper oxide. Here's a little piece of it, YBCO as we call it. It's a little ceramic. And it has a property that if you cool it, if you dump it in liquid nitrogen, it becomes a superconductor. And that's why it's called a high temperature superconductor, because liquid nitrogen is a relatively high temperature as far as these things go. So here's a little piece of this YBCO crystal, which has just been dumped in liquid nitrogen. And here's a track of magnets. And if you push it, because it's a superconductor, float on top. Unfortunately, it crashes there. I'm sure you can all guess why it crashed. Well, because it heated up. It's not cold enough. And then it loses its superconducting property. So when you keep it cold, it will just keep going forever, really. And it's a direct the superconductivity is a direct the ability to float over magnets is a direct consequence of its ability to have electrical currents flow without any resistance. Okay, so this is something very real, something that you can do all these kinds of fancy experiments with. And the hope is that someday this will appear in all kinds of applications involving transmission of power, solar energy, in computers of various types. This particular application is very much current. Its superconductors, not precisely YBCO, but related compounds, are in these MRI machines that you see in hospitals today. So superconductors are very interesting, of great practical importance, and really the question that keeps people like me awake at night is how to make better superconductors, which will perhaps go superconducting at even higher temperatures. But here I want to just talk about some basic properties of the electrons in the superconductor. And the message I want to get to, the understanding we've achieved over the last 20 years, is that for some crucial properties of these materials, again, we have to worry about quantum entanglement. But it's not just simple entanglement of two electrons like in a hydrogen molecule, but a much more complicated type of entanglement, which also is long range, over an appreciable distance in the crystal. And exactly what that entanglement is and how do we describe it is very much a problem of current research. We don't, in some sense, even have the complete language for it. But I'm just going to give you just like a pictorial flavor of what this entanglement is. So here's the kind of things we love to draw. These are phase diagrams. We don't have to go into all the details here. The horizontal axis, the density of electrons in this particular layer in the crystal, and the vertical axis, the temperature. And the important phases I want to talk about here are the AF, which is called an antiferromagnet, the strange metal, and the superconductor. So the piece of IBCO I showed you was somewhere down here, and had this property of floating over the magnets. Okay, so we know a lot about what's really going on and where the electrons are sitting in this material. In particular, if I take this antiferromagnet, the electrons have a very simple configuration. So first of all, the coppers live on the vertices of a square lattice. And then furthermore, on each copper, there's one active electron. So we forget about all the other electrons. And this electron has this particular arrangement of spins, where half the electrons are spin up, say on the black squares of a chessboard, and the other half are spin down on the white squares. And this is really actually what they do on their own. If you just take this crystal and you go with this density of electrons, you can go in and measure at various laboratories around the world and conclude that the electrons are in this state, this staggered state. We call it an antiferromagnet. And this is not an entangled state because each electron has a definite orientation. It's not entangled with any other electron. Let's not go there. It's not important for my talk. Sorry about that. I should remove the DW. All right, so that's another picture of this antiferromagnet. Now, as you change the density of electrons, you remove a few electrons. And what happens on their own, and for reasons we're still trying to understand, the electrons start to entangle with each other. And I'm just going to show you a few pictures of entanglement. So you can now imagine the electrons form little hydrogen molecules where they just pair up. So here's one electron on a copper here, another electron there. Neither of them is spin up nor down, but they form this state that I showed you earlier that appears in a hydrogen molecule. Okay, so the electrons then pair up like in a hydrogen molecule. And now you can imagine a situation where these pairs start to move around. And they move very freely. Now the pairs have a property the pairs behave as particles called bosons. So I don't have time to explain what that is. But it turns out this Bose property of these pairs of electrons is what's responsible for superconductivity. Because these pairs can move freely and all occupy the same state at low enough temperatures. So that's not entanglement, that's just superconductivity, and Bose condensation. But if you ask the question, why is it that the superconductivity appears at really high temperatures here? It's because this picture is incomplete. And you can imagine a somewhat more complicated type of phenomenon, where if you now look at these 4 electrons here, right now, this electron is entangled with that one, and this one with this one. So what happens, we believe, is that these electrons can exchange partners there. So they were this way and then that way. So this you can think of as kind of a higher level of entanglement. You had one electron entangled with this one electron entangled with this one. But now these entanglements itself, these bonds, can exchange positions. So now this is entangled with this one, and this is entangled with this one. So really, all 4 are entangled. They're in this particular state, the kind of state that appears in a benzene molecule, if you're familiar with that. So that's called resonance in chemistry, and here it's something that's happening in this picture, between 4 electrons on this square. But really, it can happen all over the place. And through lots of these processes, you see that all the electrons start to get entangled in some very complicated wave function. And really, the challenge of our field is to describe this process, describe this long-range entanglement appearing between electrons. And it's very clear from many, many experiments and a lot of work by people in the field that this kind of entanglement is the key to understanding why this is a good superconductor. Okay, so I'll just leave it at that. Finally, how am I doing on time? Yes, let me just, okay, this is a good point for questions. Go ahead. Yes. Okay, so the question was, I said in the beginning that entanglement is monogamous. Do you imagine a big orgy here? Okay, that's rather colorful language. So I think the better way to think about it that yes, entanglement is monogamous, but it can be hierarchical. That is, you should think of these pairs forming and then the pairs entangling and so on and so forth. So there's a precise sense in which it's monogamous, but it can build up still to large distances. Yeah.
Very high temperature superconductor. Why
yes.
is that?
Okay, so there it's probably because the nucleus of the hydrogen atom is so light that it oscillates a lot, and there's a more conventional theory of superconductivity where it's the vibration of the lattice that induce pairing of the electrons. That doesn't really require entanglement in any fundamental sense. And we believe in hydrogen that's probably the mechanism. It's just the fact that the nucleus is just a single proton. It's the smallest nucleus you could imagine.
It's not a strange metal. It wouldn't be a strange metal.
As far as we know, I mean, this has not been all sorted out, but that would be my expectation. Right.
Okay.
Okay, so, yes, okay.
How did you get the Cooper pairs formed in the first place?
I just gave you I just drew some pictures of what we think is going on. But what causes them to do this? Well, we believe it's the nature of the interactions between the electrons. In this particular crystal structure, it turns out that the interactions between the electrons favor this configuration. And that's precisely the question we try to answer.
You said initially they were not.
They were not entangled in the antiferromagnet here. So really, operationally, all I did was remove some electrons. And then the electrons by themselves, at that point, once you removed a few, they decide on their own to entangle.
How much do you have to remove?
Okay, great. So this will tell you. So you have to remove about 10% of them. Yes?
Do you have reason to believe a room temperature superconductor is possible?
I don't have any reason to believe it's impossible. Let me put it that way. It could happen, but I don't have a calculation that proves it must happen. We don't know. Yeah.
I was just wondering if those Einstein condensates, if the fermions actually have integer spin, or?
Well, the pair of them has integer spin. The pair, the single electron is still an half integer spin. All right, so let's go on. This is great. So everyone's with me. I'm going to have to skip a few things here, but all right. So really the place where, as far as where we have the biggest mystery, is in this thing called a strange metal, which is above the superconducting temperature. And you might wonder, okay, there's a strange metal, why do we care about it? Well, what we really care about fundamentally is to make this critical temperature for superconductivity as high as possible. And the only way we're going to figure out how to do that is if we understand what it goes into. So if we understand the strange metal, then we have a hope of knowing when the strange metal will give way to the superconductor. So it's really, without an understanding of strange metal, I think most people agree, we're just never going to understand the superconductivity in a fundamental way. So it's because, for that reason, many of us have been obsessed by the strange metal, even though it has no conceivable application as far as I know. Maybe it will someday, but it will, we think at least theoretically it will lead us to a much deeper understanding of these very useful compounds. So I won't say anything more in detail except to say that it has a lot of strange dependencies in temperature of various properties that you measure here. So if you compare this to an ordinary metal like copper or silver or gold, various properties have a rather strange temperature dependence. And the only way we can conceive of understanding those is by invoking this long-range collective entanglement of the electrons. Okay. So I think I'm going to skip this part because I had so many questions, and this is a bit more technically involved. Let's see. All right, so this, in an ordinary metal, you don't have entanglement. And the idea there is, a metal is made up of lots and lots of electrons, but when the dust settles, what's carrying the current is not just a single electron, but an object we call the quasi-particle, which is an electron surrounded by a cloud around it. So if you don't look too closely, it just looks like an electron. So that's why we call it a quasi-electron. And this picture of quasi-electrons is really at the heart of all our understanding of the properties of ordinary metals like silver or copper or gold. On the other hand, in a strange metal, this doesn't work. So that's really the defining property of a strange metal, that there are no quasi-particle excitations. And one consequence of this, very much like the black hole I mentioned earlier, is that the behavior of this metal as you perturb it becomes very chaotic very quickly, that it just becomes thermal, just like a black hole became thermal in this very short time, which was the inverse of the Hawking temperature. So it turns out that there is a kind of a time it takes for the electron to become chaotic, and it obeys the same expression that I showed you earlier for the black hole. It's the inverse of the temperature, in this case of the strange metal, not the black hole, where it's Planck's constant over the absolute value of the temperature. Okay, I'm just going to go, all right. Okay, so that's my summary of strange metals, and I see I have a few more minutes left. So now I want to put forward in some sense, some of the most surprising result that's appeared in the last few years. So I've told you about the central idea of quantum entanglement, which not only affects, now we know, the properties of astrophysical objects like black holes with long-range entanglement, but also produces these very strange metals which have strange properties as a function of temperature, because the electrons, in some sense, lose their identity. In most metals, the electron it becomes a quasi-electron, but here it just disappears. It just becomes a soup entangled with all the other electrons. And if you then look at the properties of this quantum soup that's present in both black holes and strange metals, we find that there are some remarkable similarities in how this time to chaos depends on temperature. Okay. So now the last part of my talk, I want to introduce a particular, what we call a toy model. It's a model, not a model of anything real, but it's a model that we physicists can solve. So it's just a set of thought experiment, much like Einstein's thought experiments, if you wish. And this model is both a strange metal and a black hole. Okay, so I'm going to show you a few pictures of it and try to give you an idea how something could both look like a strange metal depending on how you look at it. And if you look at another way, it looked like a black hole. So there's a dual description of this model, which shows you that there's a seeming, the strange similarity between black holes and strange metals, and the presence of long-range quantum entanglement is something really fundamental. And you can even get a little toy which looks like both. All right, so let me describe the toy. So you take a bunch of sites. So this model is, people are calling the SYK model, so I'm happy to go along with it. It's a model, a variant of which I proposed with my student Jin Wooye in 1992, and Kitev simplified it in a way that allows many more calculations to go forward. Okay, so just pick some random position. So this is a thought experiment. I'm going to imagine that I can, in my laboratory, create this sort of configuration of electrons. So I pick lots of random positions. It doesn't matter, put them on a plane if you wish. And then occupy a few of them with electrons. Okay, so you put these electrons here, and they now want to start to move around. Okay, now in a normal metal, each electron, would just move on its own. This electron would start hopping around here from side to side, and the other electrons would hop. So there'll be each would become a quasi-electron, and you'll get an ordinary metallic behavior. But I'm going to imagine that I'm the one who sets the rules. So this is a thought experiment, really. Imagine that you forbid each electron to move on its own, but only allow it to move when it has a partner. So in some sense, this will be a toy model that has nothing but entanglement, as you'll see. So for example, those pair can move from, they can go from here to there. They move together. So you pick 2 electrons at random and move them randomly anywhere you want. And that's the full definition of the model. So allow everything to happen randomly, but only allow electrons to move in pairs. And that's the SYK model, really. So those 2 can move randomly there, there. So there's really lots and lots of possibilities. They all can happen, and they all happen with the amplitude, which is a random number. Okay, that's it. That's the model. And people are thinking about how you might make such a model in the laboratory. Basically, you take a bunch of electrons in random positions and allow them to move anywhere, but forbid them to move on their own. They need a partner. That's it. So they have to entangle with somebody to move. So in the moment these 2 electrons move from there to there, they're entangled with each other because really they're both here and there, but really together. Yeah. No, you can pick. That's right. That's key. Right. So these two now, that particular electron here can now entangle with this one or anyone. You pick 2 at random and move it randomly to any other side. That's the definition of the model. Okay. I have a few more. So it has nothing but entanglement. And it turns out this is both a strange metal and a black hole. Well, you could sort of see why it might be a strange metal. These electrons are going nowhere in particular, and they always need a partner. And so their motion is very much, very different from the motion of electrons in an ordinary metal, where the electron just acquires a cloud and moves, on a straight line roughly. There's no such thing happening here. So it looks like if I measured the current in this object, I'll get all kinds of strange properties. That doesn't seem totally ridiculous. What does seem ridiculous is this is a black hole. So how is this a black hole? So for the experts, this is the actual way you write it down. It's just a 4-fermion Hamiltonian with a random number. But I just told you in words what these equations represent. So here's the picture of the SYK model. Okay, so now I imagine I have this model of electrons can only move in pairs, and this is some spatial direction x. Now it turns out that this model is equivalent to theory of gravity, and that's just Einstein's theory of gravity. But that theory of gravity lives not along this direction x. It lives in a curved space with an extra dimension. Okay, so this zeta is some new dimension of space. It's what we call an emergent space, and space is curved along that direction. And at the very end of this emergent direction, there's a black hole. Okay, so now I have two very, very different looking theories. On the one side is this SYK model I just described. And the other side I have Einstein's theory of gravity in this particular curved space with an extra spatial dimension, which has now become quantum mechanical. I have to take Einstein's theory and quantize it. Apply the principle of quantum mechanics to Einstein's theory, which we now know through the work of many people in the last 20 years how to do in these particular types of spaces. And it turns out those two theories are the same. It just depends on what particular property you're measuring and how you're measuring it. In some respects, it looked like a theory of gravity. In other respects, it looked like a strange metal. And in fact, in particular, really, you could compute properties of this black hole, like do the calculation that Hawking did for the property of this horizon, and you can deduce things like electrical resistivity of this strange metal. So there's a deep connection between these two different pictures. It's called a duality. This is that appears in many different contexts in physics. Here, there's a duality between gravity and a strange metal. But it really requires that the theory of gravity have an extra dimension. All right, so I can't really say much more than that. Yeah. So the basic idea here is entanglement, when it's of the right type, can change a system which is living in this case, one dimension, to a system that's living in two dimensions, two spatial dimensions. So you can have an extra spatial dimension. And this is another deep idea that's emerged actually from string theorists in other contexts, which also finds its realization over here. So let me try to give you, some understanding of what this means. Why this is our best understanding, really. This is something very much a topic of much research and something that's even work funded by one of the Simons collaborations. So here's a picture that tries to make sense of this. So here I have, say, my electrons. The electrons are sitting here, and this is the x coordinate. I've just projected it down to a line. And then the electrons start to entangle with each other. So say this electron entangles with that one. That's what the blue square represents. Okay. And then as the question asked, well, these are monogamous, but entanglement can be hierarchical. So these blue squares can also entangle with each other. That's, if you wish, what these red triangles are, telling you the entanglement between the blue squares, and so on. And the red triangles can entangle to the blue squares, and so on and so on and so forth ad infinitum. So there can be an infinite hierarchy of entanglement, and we can think of this direction as what you call depth of entanglement. So that's really what happens when you take a system that's very strongly entangled. This extra coordinate that I'm writing down as just some depth of entanglement becomes like a spatial coordinate. It behaves just like a coordinate and extra coordinate in Einstein's theory of gravity. That's the best I can say. And the SYK model is a particular model where you can prove pretty much that this is what happens. And this then allows you to take properties of black holes and say interesting things about strange metals and vice versa. And the common thread that's bringing them together is this idea of long-range entanglement. Okay. Here's another picture. You may have heard of string theory. So you can also think of entanglement as coming for the fact that the particles which are living in this low-dimensional space, the blue particles, are entangled, and what's causing the entanglement are these strings. And the strings end on the space that you're sitting here. And so these strings are moving in 2 dimensions where the particles are in 1 dimension. And that's another way of understanding why a theory of gravity, which is what strings describe, is in a higher dimensional space than the theory of entangled particles, which is sitting in this one lower dimension. Okay. So that's the kind of the amazing new idea that's a focus of much research in theoretical physics in the last 10 years or so. That quantum entanglement, rather than being a kind of a philosophical sidelight that Einstein first focused on in the EPR paradox, has very important consequences for black holes, as Hawking first described, and is playing a central role in our understanding of complicated materials like the high-temperature superconductors. And finally, it also, quite amazingly, for the right type of strange metals, lead to this phenomenon of emergent spatial dimensions, where depending on exactly which regime you're working in, the space would look like it's 1-dimensional or 2-dimensional. But there's really a duality between those two descriptions once you include the quantum fluctuations of space-time into account. Okay, so thank you very much.